Think about biting into a raw green village lemon. Your mouth immediately puckers from that sharp, sour taste. Now compare that to washing dishes with an ash filtrate, the kind used to cook local vegetables like boo or gabe. The water feels incredibly slippery and soapy against your skin. Those distinct physical sensations are your introduction to chemical opposites. The sourness points to an acid, while the soapy texture points to an alkali. We obviously cannot taste or touch unknown chemicals in a laboratory to figure out what they are. Instead, chemists use safe indicators, like litmus paper. To remember the reactions, we rely on a simple mnemonic. Acids turn litmus red, and bases turn litmus blue. You will often hear the word base used in these situations. All alkalis are actually bases, but an alkali is specifically a base that has the ability to dissolve in water. Recognizing these physical properties and color changes gives us a reliable way to categorize the substances we interact with every day. Categorizing a chemical is helpful, but handling it safely requires knowing exactly how strong it is. This chart shows the pH scale, a precise metric running from 0 to 14. The exact middle, 7, represents a completely neutral state. Let's plot some familiar local items here. A bottle of pure Rwenzori drinking water sits right at the neutral 7. A green lemon lands around a 3. A block of washing soap registers at a 9. But avoid this common trap. As you move lower on the numbers toward 0, the acid gets stronger. A pH of 2 is significantly more corrosive than 6. On the opposite side of neutral, the rule flips. As the numbers climb higher toward 14, the alkali becomes stronger and equally dangerous to handle without care. The pH scale replaces guesswork with a specific mathematical map telling us exactly what kind of chemical intensity we are dealing with. Once we can measure these extremes, we can use them against each other. This equation shows a neutralization reaction. When you mix an acid and an alkali together in the right amounts, they react to cancel each other out, leaving behind two entirely different, harmless products, a salt and water. This infographic shows how we apply that equation in agriculture. When farmers in Kabale notice their Irish potatoes struggling in acidic soil, they introduce slaked lime, a base. The soil chemistry neutralizes, and the crops recover. This diagram illustrates the exact same process happening in the human body. When your stomach produces excess hydrochloric acid, causing the pain of heartburn, swallowing a magnesium hydroxide antacid tablet neutralizes that excess acid to provide immediate relief. Now consider a first aid scenario. If you are stung by a bee, the venom is mildly acidic, so you treat it with a mild alkali like baking soda. But a wasp sting is different. It is naturally alkaline. Based on what you know about chemical opposites, pause the video right here. What common household liquid would you apply to a wasp sting to neutralize it? Neutralization allows us to actively correct chemical imbalances in our environment by introducing the precise opposite. Let's see if you solved the wasp sting problem. This diagram shows the correct treatment. Because the wasp sting is alkaline, you must apply a mild household acid, like vinegar or lemon juice, to achieve a neutralization reaction and stop the pain. By identifying the core chemical problem, an alkaline venom, you were able to balance the equation by selecting its exact chemical opposite. This table summarizes the core properties we have covered. Take a screenshot of this matrix to use as a study guide. It captures the contrasting tastes, litmus reactions, and opposite directions of the pH scale, anchored by the central neutralization equation. Chemistry extends far beyond the walls of a laboratory. By understanding how acids and alkalis interact, we have the practical tools to correct acidic soils, soothe painful stings, and pull dangerous extremes back into a safe, neutral balance.